Okay, welcome to part B of the paper then. Let's try and get through this one as quickly as possible. Ammonia then, an important chemical used to make fertilizers made in industry by following the equilibrium reaction as shown there. Write down the value of the standard enthalpy change of formation for ammonia. Now this one is all about you knowing the definitions of these enthalpy changes. You should know that the enthalpy change of formation is the energy change or the enthalpy change when 1 mole of a substance is formed from its elements in their standard states. Now that's just for the formation of 1 mole of a substance. Now if you look at this equation here, they have given you an equation that forms 2 moles of ammonia, and the energy change for that reaction, notice that they've used just the R symbol there because it's just for this reaction as written, is minus 92 kilojoules per mole. If we want the energy that in this case is released for the formation of 1 mole of ammonia, it's going to be half of that. Now it wants the unit as well, and we need to be careful to include the signs. So it's minus 46 kilojoules per mole. State what's happening to the forward and reverse reactions once equilibrium is reached. Well, you should know that in a dynamic equilibrium, the reaction doesn't stop, but the rate of the forwards reaction is equal to the rate of the backwards reaction. I'm not going to write everything down, so we can get through it a little bit quicker. But that's all that they wanted there. They wanted to know that the rates of the forwards and backwards reaction are the same. Now, the data in table 21.1 shows the equilibrium percentages of ammonia formed under different conditions of temperature and pressure in the presence of an ion catalyst. So what you've got here, you've got two different temperatures in Kelvin, pressure measured in atmospheres, equilibrium percentages of ammonia. So it means when you get to equilibrium, what percentage of that reaction mixture is ammonia. So obviously the higher number there means the position of equilibrium lies more to the right. You've made more ammonia, you've gone further, you could say, towards completion in this reaction. Realise I might have been covering the microphone there, but we'll see. So this question here then, they want you to plot on graph paper the results and draw lines of best fit. Now remember, lines of best fit, just like at GCSE, are going to be curved lines of best fit, although they will allow, in the additional guidance here, point to point. But yeah, it should be a curve. But the key thing is here, they got 3 marks. Now, we need to know that we need to be using more than 50% of our graph paper. This is the graph paper that we've been given here, and that's for the plotted area. You can't just extend your axis to numbers that don't matter or don't impact. We should be doing it in pencil, and we should be using a ruler and drawing it as neatly as precisely as possible. And we should be plotting the points to within a decent degree of accuracy. So what have we got? I'm just seeing what degree of accuracy they want. It's usually sort of like a half a small square is what they're after. So we've also got to work out what's going on our y-axis and what's going on our x-axis. Now remember, you've got to think about independent and dependent variables. So the thing you're changing is the independent variable, and that goes on the x-axis. And the thing that's changing as a result of that is the dependent variable, and that's going on the y-axis. So what we've got here, the thing that we're changing is the pressure, and we're looking at the equilibrium percentages of ammonia at those different pressures, but also at 2 different temperatures. What that means is we're going to have 2 different lines here, one that's going to represent the data for 473 Kelvin, and one that's going to represent the data for 673 Kelvin. Both cases, pressure is going to go on the x-axis and equilibrium percentage of ammonia is going to go on the y. So I would label your axes, so pressure, and this is in atmospheres. You can put it in brackets or you can use the forward oblique, solidus as my old physics teacher used to call it. And then we've got equilibrium percentage of ammonia, and that's just a percentage. Now we've got to choose axes that are appropriate. So if we look at our pressure scale is going from 10 up to 1,000, so essentially 0 to 1,000. So we are going to start at 0 in this case. Counting the squares, it looks as if we should probably go 200, 400, 600, 800, 1,000. I appreciate some of you may have only been able to sketch this, but just make sure that you know sort of how to choose decent scales. Obviously, you would have done that with a pencil and a ruler. So you would have gone 0, 200, 400, 600, 800, 1,000. Remember, had we not started at 0, so let's say the data, I don't know, let's say it started at 500, we wouldn't have had to have started at 0. We could have put in a broken axis there, or just literally started labelling, say 500, 600. Do it to maximise the plotted area. Okay. Equilibrium percentages of ammonia, they go down as low as 3.9 and as high as 98.3. So we're probably, we've got a line up here, we're probably going to have to do 20, 40, 60, 80, and 100. And because we're not going to use this data for anything else, what I'm going to do is I'm just going to go straight from the mark scheme. And the mark scheme shows one line that goes like that, one line that sort of goes like that, okay? And then we would want to label these. So this is our one here at 673 Kelvin. This is our one here at 473 Kelvin. Okay, so it should have ended up looking something like that. So it should have been a relatively straightforward 3 marks there, okay? Maybe you just got your axes the wrong way around. It says, how would the plot for 673 Kelvin be different if the iron catalyst had not been used? Now remember, what this is showing you a plot of when the system has reached equilibrium. So it's showing you the percentage compositions at equilibrium. We should know that a catalyst, although it speeds up reactions, it speeds up the forwards and the backwards reaction by the same extent, which means that the position of equilibrium that's ultimately achieved is exactly the same. It just means that the reaction gets to equilibrium quicker. So how would the plot differ? There would be absolutely no difference, and you're going to get a whole mark for that. And then you get 1 mark for saying that the catalyst doesn't affect the position of equilibrium. Or words to the effect there. So for instance, if you said it doesn't affect the position of equilibrium but speeds up the rate at which you get there, it speeds up the forwards reaction to the same extent of the backwards reaction but doesn't alter the position, fine. My advice there would be always, though, to refer back to the position of equilibrium, because that is your direct measure of your yield or your equilibrium yield. Position lies to the right, high yield; position lies to the left, low yield. Explain why the yield is greater at higher pressures. As soon as it says explain to do with equilibria, you're just thinking Le Chatelier's principle. So you're just thinking, if I change the conditions of a system in equilibrium, how does the position of equilibrium move to counter that change? Well, at higher pressure, let's have a look at the equation again. How do I put that page? Not very useful. But if we think about pressure, what we're thinking about is number of moles of gas on both sides of the equation. On the left-hand side of the equation here, 1 mole of nitrogen, 3 moles of hydrogen. So we've got 4 moles of gas on the left-hand side. On the right-hand side, 2 moles of ammonia, so we've got 2 moles of gas. So if we were to increase the pressure for this particular system in equilibrium, the position of equilibrium will move to the side with a fewer number of moles of gas will move to the right, and the yield will increase. So explain why the yield is greater at higher pressures, and we would say something like more moles of gas on the left-hand side, therefore an increase in pressure, and I'm doing this in shorthand, write it out of course, increase in pressure would lead to the position of equilibrium moving to the right, which will obviously then increase the yield. Now, it's only 1 mark, so we're not going to have to go through that whole thought process, but I would always link it back right at the end to the yield, because the question has said yield. If you just say position of equilibrium, you've not strictly speaking answered that question. Right, so now I think we can... now we can put it on the floor. Right, so a student says that an industrial firm carrying out the reaction at 473 Kelvin would not use a pressure above 400 atmospheres. Discuss the student's statement. So these are these really annoying ones that come up in the module test as well, the discuss, and you don't always know what to do. The first thing to realise is discuss doesn't necessarily mean that the student is correct. Okay, I think we can answer this based on the student is correct, because they're not going to use above 400, and I do actually have a question. Here it is. They're not going to use above 400, but actually you could argue that they would go above 400 if you like, if you do that effectively. But if we look at this, so it's saying 473, so this column here, we're not going to go above 400. Well, at 400, we've got nearly a 95% yield, which is amazing. We would have to increase the pressure a considerable amount to just push it up a couple more percentage points. Now remember, high pressures, 400 times atmospheric pressure. High pressure, the way that you generate that is you pump the gas in and you keep pumping using a lot of energy, so high costs there. And then you've got to maintain that pressure. So you've got to have reaction containers that have got really thick walls, which again is really expensive. And you increase the risk of some sort of rupture and explosion, and it becomes very dangerous. So for all of those reasons, no, you probably wouldn't go any higher than 400. So you could give reasons like the yield is nearly 100%. So it's not needed, something like that. And to increase the pressure would increase the cost or make more dangerous. That's nice, dangerous, sorry. Because, just qualify that. The good wording to use with pressure is that it's expensive to generate and maintain high pressures. It's good wording. Right, then the last two in this question then. So it says ammonia is not often made at temperatures below 473 Kelvin. This is because the equilibrium is established too slowly at lower temperatures. Explain why the rate of a reaction increases with temperature. So this is a lovely question because it's absolutely nothing to do. Okay, we don't need that, but my phone's ringing at the same time. Now we're live again. Yeah, this is a lovely question. It's nothing to do with this equation here. It's just a very, very general question. Explain why the rate of a reaction increases with temperature. And you could have done this at GCSE. So if you increase the temperature, firstly think what effect is it going to have on the particles in the system. It's going to increase the average kinetic energy of the molecules, particles, whatever you want to call it. And then remember there's those two effects. Number one, it means those particles are going to collide more often. But at A level, we learned that actually that's only going to account for about a 1% difference. 99% of the difference is to do with more of those collisions having the necessary energy to be successful. So having energy equal to or greater than the activation energy. So we would say greater proportion or just more is fine of collisions. And they're actually going to allow in the mark scheme here just to say successful. I would go down the route of saying having greater than the activation energy. I think that's a far safer answer here. Okay, so the equilibrium shown is set up. The data below shows the composition of an equilibrium mixture. Calculate the value of Kc. So remember Kc is equal to the product of the concentrations of the products raised to the power of the molar ratios in the reaction divided by the product of the concentrations of the reactants raised to the molar quantities in the equation. So, products over reactants. Products, we've got NH3 here, but there's 2 moles of it, so it's the concentration of ammonia squared over the concentration of nitrogen multiplied by the concentration of hydrogen cubed, because there's 3 moles of it. So all we're simply going to do is we're going to drop those numbers in, square them or cube them first, and then arrive at our answer. Okay. You arrive at the answer and it's not asked for units and it's not giving units. At AS we don't need to be able to do the units. At A2 we will have to do the units, but the units are quite straightforward because we know the units of concentration are moles per decimeter cubed. So on the top we've got that term squared. On the bottom we've got moles per decimeter cubed, and then we've got moles per decimeter cubed 3. Okay. What you can then do is you can cancel these indices, like you'd ordinarily do in maths. So I'll cancel one of those moles per decimeter cube, and then I'll cancel the other one. So we've got 1 over moles per decimeter cubed to the power of 2. So we could say that moles per decimeter cubed -2, so moles to the -2 dm to the -6 would be the units. Okay, but we'll do that sort of thing at A2. Just pause there a second. Okay, next question. Barium oxide, BaO, was once used to make oxygen gas. When heated above 500 degrees, it combines with oxygen from the air, so there's going to be other gases in there as well, to form barium peroxide. Above 700 degrees, barium peroxide decomposes to give barium oxide and pure oxygen. Okay, the removal of carbon dioxide from the air enabled the cycle to be carried out many times. Suggests why the removal of carbon dioxide was necessary. Well, in this case here, carbon dioxide doesn't figure in that equation there. So what we haven't got is its concentration affecting the position of equilibrium or anything like that. We can only presume that it could potentially react. And what could it react to form? Well, we learn within Elements of Life about group 2 oxides and carbonates. And carbonates decomposing to give oxides, or oxides reacting with carbon dioxide to form carbonates. So what could happen is, if you've got carbon dioxide in there, is that the barium oxide could react with the carbon dioxide to form the barium carbonate. So in short, you would say that CO2 could react with barium oxide, and in fact it could react with the barium peroxide as well, you know the reaction with barium oxide reacting with carbon dioxide to form the barium carbonate, just the reverse of the decomposition. Okay, barium oxide is made by heating barium carbonate, so we can thermally decompose. And in fact, look, there's a little clue as to what could happen, the reverse of that reaction essentially. How does the thermal stability of barium carbonate compare with the thermal stability of calcium carbonate? So this means you heat it, and you know which ones you need to heat to a higher temperature or for longer, with the same sort of Bunsen flame, that sort of thing, in order for this decomposition reaction to take place. So let's just have a little look at these two then. So let's compare calcium and beryllium carbonate. Both are ionic compounds. They'll have both barium and calcium are in group 2, so they'll both form 2+ ions. And then you'll have the carbonate ion, the CO3 2- ion. Now, in calcium carbonate compared to barium carbonate, barium is in period 6, whereas calcium is in period 4. So the calcium ion is going to be smaller than the barium ion. What that means is there's a higher charge density on calcium ions than on barium ions. So the same charge, 2+, but in a smaller volume, which means it gets closer and attracts and polarizes or distorts the carbonate ion more. Now, I'm going to draw one representation of the carbonate ion with these sort of delocalized bonds, but ultimately it's 2-, okay? And one of these carbon to oxygen bonds we can draw as pointing towards the calcium ion. We can do exactly the same with the barium ion. Now, this one, because it's got a higher charge density than this one, is going to polarize or distort this carbonate ion more than this one. So what it means is the electron density in this bond here sort of gets sucked towards the oxygen to the extent that carbon dioxide can drop off and leave with the oxygen with those 2 electrons and a 2- charge. Similarly here, that could happen too, but because this has got a lower charge density than the calcium ion, you don't get as much distortion or polarization of this ion, and therefore you need to heat it to higher temperatures in order to get the carbon dioxide to snap off and leave you with an oxide ion there. Okay, so that's the gist of it. So what we've seen here is that you would need to heat barium carbonate to higher temperatures. It would have a higher thermal stability. We've got to get 4 marks out of this. So how does it compare? And then explain. So we're going to get 1 mark for the how. So something along the lines of barium carbonate is more thermally stable. Then we've got to go down this idea of sort of like charge density. So we would say something like both ions have a 2+ charge, but the barium ion is larger, therefore has a lower charge density. So we're going to get a mark for the charge density, we're going to get a mark for the larger ion, and therefore the barium ion distorts or polarizes the carbonate ion to a lesser extent. Now, you can then say, therefore, meaning that it's harder to decompose the carbonate ion into an oxide ion and carbon dioxide, but that's not necessary for the marks here. The mark schemes pretty much always want those points on them. Once you've done a few past papers, you get to see what they're going to give you the marks for, and then you keep to those because it's time efficient. Okay. You can of course give the reverse argument, and it'll often say that in mark schemes. So it'll say ORA or reverse argument. So you could say, for instance, calcium ions are smaller, therefore higher charge density. They distort the ion more. So you just argue it the other way around. Why is it valid to compare barium carbonate with calcium carbonate? So remember, valid is if you're going to get results that are both reliable, accurate, but also obtained from a fair test that's designed to test the actual thing that you're investigating. It's a bit of an odd question, this one, but in essence, whenever you get a group 2 question, there will be part of that question that's coming from the part of the syllabus that's asking students to be aware that if you're in the same group of the periodic table, you have similar reactions or similar properties. Ultimately, this is the stock answer. Oh, barium and calcium are in the same group. Okay, or you could say they both form 2+ ions. That's all that question is after, but I can understand if you're a bit confused by that one. Next one, barium oxide dissolves in water to form barium hydroxide, so it'll form an alkaline solution. So in a titration, 25 centimeters cubed, a solution of barium hydroxide reacts with 23.6 centimeters cubed of 0.12 mole per decimeter cubed HCl. First, you write the equation. So we've got barium hydroxide, and it's not asked for state symbols, so we don't have to give state symbols if they don't ask for it. There's going to be no mark for that. In fact, there's only 1 mark. Plus HCl, so we've got an alkali and an acid, or a base and an acid. We're going to neutralise, and we're going to form barium chloride as the salt. Just remember though, barium's in group 2, chlorine's in group 7, so we're going to have 2 chloride ions for every 1 barium ion. And then as it's a neutralisation reaction, we're going to form water. But we've got 2 oxygens on this side, so we're going to have 2 oxygens on that side. I've now got 4 hydrogens and 2 chlorines. I've got 2 hydrogens there, so to get me 2 more hydrogens and 2 more chlorines, I put a 2 there. That's going to be critical for this next bit here. Calculate the concentration of barium hydroxide in moles per decimeter cubed. Now you don't have to do this, but you never really go wrong doing this. A titration, 25 centimeters cubed of a solution of barium hydroxide. So we've got the barium hydroxide in here. Okay. The volume, now I'm going to put that in decimeters cubed to start off with, just so I've done my my conversion straight off. We do not know its concentration, and we don't know the number of moles in there. We're titrating that against a solution of hydrochloric acid, and we know that the volume of hydrochloric acid required to neutralise all of the alkali in there is 23.6 centimeters cubed. So divide that by 1,000, 0.0236 decimeters cubed. And we know that the concentration is 0.12 moles per decimeter cubed. Now, if you do it like this, you've extracted all the information from the question, you've put it into a place where you can easily see, well, I've got 2 values, so I can calculate a third here, but I've only got 1 there. So the only thing I can work on is my HCl. So my first step is the number of moles of HCl, and the number of moles of HCl is equal to the concentration times by the volume. And I would write down C and V, or conc and vol, to help the examiner see what you've done, especially if you don't get the right answer. The concentration is 0.12, and I've already changed the units, so that's lovely. And so just do that on my calculator. 0.12 multiplied by So I've got 2.832 times 10 to the minus 3. You don't need to do it in standard form, it's just how it's popped up on my calculator. And that's the number of moles of HCl. Now what we can see from here is that 2 moles of HCl react with 1 mole of barium hydroxide. So therefore the number of moles of barium hydroxide are equal to 2.832 times 10 to the minus 2 divided by 2, okay, which is 1.416 multiplied by 10 to the minus 3. And now I can do the concentration of barium hydroxide. By the way, some people like to go back and fill these in as they go. Don't have to, but in complicated titrations, sometimes quite good. Also good if you ever want to go back through and check your answers that you've done it the right way, so you can glance back through if you feel that time's going all right in the exam. So we've got this number of moles. So concentration is the number of moles divided by the volume. So 1.416 times 10 to the minus 3 divided by 0.025 divided by 0.025. So I've got from that 0.05664. Now I can write that all down if I like, or I can round appropriately. Everything I've been given here is to 3 significant figures, so I can go 0.0566. Let me just check. Yeah, cool, lovely. But I would always stick this down, because then if you round too harshly, they will give you the mark because they've seen that you've got this, okay? What you don't want is to not get the mark just because of a rounding error. So I'd write down all the decimal places and then do a final rounding step, okay? And calculate the concentration in grams per decimeter cubed. So what it's asking us to do is to go from moles per decimeter cubed to grams per decimeter cubed, and a lot of people get fooled by this, but it's very, very straightforward. We know here that there's 0.0566 moles in every decimeter cubed. So if you've got 1 decimeter cubed, you've got that many moles. The question is then essentially, what mass would that be? The decimeters cubed are staying the same. We're just saying, how do we go from moles to mass? We multiply by the molar mass. So we take 0.0566. I would take the unrounded version personally. That's good if you've got that down there, or if you haven't deleted it on your calculator at this point, or use answer. Okay, and then we need to multiply that by the molar mass, which in this case, I'm reading straight off the mark scheme, is 171.3, and that gives us 9.7 grams per decimeter cubed. Okay. Right, so when ammonium nitrate dissolves in water, the process is endothermic. It's used in ice packs that are used for sports injuries, and you may well have been shown this at A-level or GCSE. So a group of students dissolve 8 grams of ammonium nitrate in 200 centimetres cubed of water. The temperature falls by 3 degrees. Calculate the enthalpy change on dissolving 1 mole of ammonium nitrate in water. So it wants the enthalpy change per mole. Give your answers in kilojoules per mole and to an appropriate number of sig figs. Underline that one so I can come back to it in a second. Okay, so we know that our equation here for the heat change or the heat transferred or H or whatever you want to say is the mass of the water that's being heated or cooled, the mass of the substance being heated or cooled, times by its specific heat capacity, times by the temperature change. Mass of the water, in this case, we assume a density of 1 gram per centimetre cubed, so we've got 200 grams of water. The specific heat capacity, 4.18, if you forget it, you've got a data sheet that tells you that. If you use 4.2, that explains why your answer might be slightly different from the mark scheme. And the temperature change here, it's gone down by 3 degrees. Now, you can incorporate the sign if you'd like, but don't worry about that too much. Just worry about the sign at the end, whether you say the enthalpy change is positive or negative, depending on whether it's exothermic or endothermic. So if we multiply those together, we get 2,508 joules of energy that has been effectively removed from that water in order to get a reduction in temperature of 3 degrees. Now that was achieved by 8 grams of ammonium nitrate. So we need to know how many moles of ammonium nitrate that was, so we can get it on a per mole basis. Okay, so moles of ammonium nitrate are going to be equal to the mass divided by the molar mass. Our mass is 8, and our molar mass, I think from memory, is 80. Let's check the mark scheme. Yeah, is 80. So we have got 0.1 moles of ammonium nitrate. If we want the energy change per mole, we're going to be taking 2,508 divided by 0.1. It's going to make 25,080 joules per mole, which is going to be 25.080 kilojoules per mole. And then we want an appropriate number of significant figures. Well, we want to go to our least precise piece of data. We've got this at 2 sig figs, this at 2 sig figs, that one at 3, so we're going to report it to 2 significant figures. It's going to be 25. And then we just consider our sign. The temperature went down. There's an endothermic reaction. The mark scheme doesn't say that you have to have the plus sign, but I would put it in because sometimes they do. Certainly, if it were a negative sign for an exothermic reaction, you would have to include it. Students want to get a larger temperature change. Some suggest using a greater mass of ammonium nitrate. That would make sense, wouldn't it? Add more of the reactant, so you've got more moles there. If we're getting 25 kilojoules for every mole, we're going to get more than 25. We're going to heat the water to a higher temperature. Some, though, suggest using more water. Well, if you use more water, then what you're going to do there is have exactly the same quantity of heat that's released, because that's dependent on the number of moles of ammonium nitrate. But what you will do is you'll spread out that heat energy amongst a greater number of water molecules. Each one will increase on average by, will have an increase in energy on average that's less, and therefore the temperature will not go up as much. Okay, so write words like that. So hopefully that was fine. Okay, this next one actually is quite tricky to get 5 marks on. So another group of students investigates the exothermic reaction between zinc and copper sulfate solution, and they've been very careful to show you that the copper sulfate solution is at a concentration of 0.2 mole per decimeter cubed. The students are provided with powdered zinc metal, and the powder is just going to make it go quicker, and solid copper sulfate solution. It's the solid hydrated copper sulfate, solid. They measure the temperature rise when 100 centimeters cubed, so they're giving you particular volumes here, which is an excess of that copper sulfate solution is used. So if that's an excess, then the zinc metal used must be less than. So in terms of the number of moles of copper sulfate, we've got a concentration that's 0.2 moles per decimeter cubed. We've got a volume that's 0.1 decimeters cubed. So the number of moles is equal to concentration times by volume. So we've got to be using less than 0.02 moles of zinc in order to do this. Okay. Design a suitable method to investigate this exothermic reaction. Well, let's just remind you what this is banging on about. You will remember, hopefully, from developing fuels, if you've got a solid reacting with something in solution, what you can do is carry out the reaction in a polystyrene cup, so some sort of insulated reaction vessel. Drop the two, put the solution in and measure its temperature with a thermometer. Add the solid, stir, and then record the highest temperature that's reached on the thermometer. Of course, the whole time it's cooling down, so you want the reaction to be quite quick, which is why we're using the powdered zinc, and you might end up using a cooling correction curve that we'll see in the next part here. But what they're asking for here is you to be really, really careful with the information they've given you in the question. So, design a suitable method to investigate the exothermic reaction. Well, the first thing we're going to have to do, we've been given solid copper sulfate solution. And so we want to make a solution to start off with. Now, it doesn't give you an indication whether they want you to calculate amounts here, and you wouldn't be wrong if you did, okay? But they're not actually going to give you marks for that. All they want you to say is to weigh out the copper sulfate solid. No harm saying using a balance. Remember, we don't use scales, we use a balance, okay? And then you dissolve that to make your 0.02 mole per decimeter cubed solution. I wouldn't know personally at this stage whether they want me to use equipment or not. I mean, they haven't gone through saying that you want to know the equipment, they just want a method. So I suppose they haven't actually said necessarily which equipment, but I don't think it's harmful to say using a volumetric flask. Okay, so we're going to get 1 mark for that, 1 mark for that. We've got 5 marks in total that we want to get out of this. Okay, then we want to add 100 centimeters cubed of the solution to the polystyrene cup. We would want to take the temperature, add a mass of zinc that's less than 0.02 moles, because they've said that it must be limiting. Okay, if you worked that out, the actual mass of zinc, that would be absolutely fine. Stir it, and then record the maximum temperature reached. And it's important that we say the maximum temperature there. Okay, so we're not just looking for the temperature change. We're going to wait until it reaches the very highest temperature change to know how much heat has been involved in that particular reaction. Okay, so quite hard and quite specific there in order to get those 5 marks. The students repeat the experiment, measuring the temperature at different times. They plot the graph shown. Use the graph to make an accurate measure of the temperature rise. Show you're working on the graph. Now, what we've got here, and again, you'll use a ruler. I haven't got a ruler to hand. But you can see that before the reaction, they've taken the temperature, and they've taken it several times, and they've added the zinc here. Okay, the temperature then rises and falls, and you'll notice that it falls at a relatively consistent rate. I mean, in fact, I've bent my line a little bit there, and I probably shouldn't. I should probably, again, take a ruler. If I take a ruler, I mean, that's terrible because I would need a ruler. But you can see that it's cooling at a consistent rate. Now, if we assume that it's always cooled at that consistent rate, which we've got no evidence in contrary, because this appears to be a nice straight line, then we can say that the actual highest temperature it would have reached would have been this here. So then our temperature change is from here to here. I would indicate that on the graph by going across here. Okay. Read off value at 3 minutes, and it should come to 24.5. So if I had used a ruler, yeah, I can see that now. Would have gone to there. There we go. So 24.5. Look at me, I got it perfect. And it started at 15, so the rise is 9.5. Okay. So write 24.5, 15, and I'd probably do 24.5 minus 15 is equal to 9.5. Okay, so you're getting 2 marks there. You're getting 1 for extrapolating the line back, no matter how you do that, just showing that you know that that's the way to do it. And then the second one is for actually doing that properly with a ruler and getting the right reading there, and then working out the temperature change. Okay, so willow bark contains salicin. Now, if you looked at the other past paper that I went through before the assessment week, this one also talked about salicylic acid and aspirin. I did say they're sort of their pet molecules. They do like them. So salicylic acid is obtained from willow bark by first hydrolyzing the salicin to salicyl alcohol, which is a solid room temperature. The structures of salicylic acid and salicyl alcohol are shown. Name the 2 types of hydroxyl group that are present in salicyl alcohol. So we've got this one here, and we've got this one here. Now this is just a standard alcohol. It's the carbon to which the hydroxyl group is attached is itself attached to just one other carbon. So you could put primary alcohol if you like, for alcohol is absolutely fine. But then this one here is directly attached to a benzene ring, meaning that the whole thing is now called a phenol group. That's what's in a medicine stuff. As is this next one. Suggest laboratory reagents and conditions for converting salicylic alcohol to salicylic acid. So if we're going from the alcohol to the acid, we've changed this primary alcohol group into a carboxylic acid. And if we change it into a carboxylic acid, we have oxidized it, and we've completely oxidized it. We've gone to an aldehyde and then all the way to a carboxylic acid. So we need an oxidizing agent. So we need acidified. It's important that we must have that acidified part, either potassium or sodium, either one. Dichromate 6 solution. That'll allow you to just say dichromate. Remember, that's that orangey solution. It's going to go green once the dichromate ion is reduced to chromium-3 ions. It tells you the oxidation of the other thing has actually happened. And we need to heat under reflux. Remember, with this, we want to oxidize all the way, so we're not distilling the product off as it forms, and we would distill the product off as it forms if we wanted to get the aldehyde product, but we want full oxidation to the carboxylic acid. So some students have an impure sample of salicyl alcohol. They wish to purify it by recrystallization from water. Give the first step in the recrystallization process. If you've not watched the other video, in that video I showed a little animation where I drew out the recrystallization process. Remember, recrystallizing involves essentially dissolving your compound and then forming the crystals again, hopefully without any impurities trapped in them. And the first step is to dissolve that, but you dissolve it in a hot solvent. So you need a solvent that dissolves your substance at high temperatures, but is insoluble at low temperatures, so you can get the crystals back. But you dissolve it in the solvent, and you don't do it in gallons of the solvent because you'll never get the crystals back. So you dissolve in a minimum amount, or minimum volume of hot solvent. So dissolve in minimum volume, and you're getting a whole mark for the minimum volume part of hot solvent. It will just accept solvent, but really we should be using hot as well. How would the students show their recrystallized product was purer than the impure sample? So again, I said this in the other paper. If we're looking at purity, then our easiest way of looking at purity is measuring the melting point or boiling point of a substance. If you've got a liquid, measure its boiling point. If you've got a solid, measure its melting point. So we would definitely measure its melting point. We're going to get it 1 mark here, so we're going to need to do a little bit more than just measure the melting point. But you'd measure the melting point, and if it's pure, then we should expect that melting point to be sharp, and we should expect it to be very close to some sort of data book value. Now, remember, for a solid, the more impurities you've got, the lower the boiling point tends to be, because it disrupts the lattice of the crystals and reduces some of those intermolecular bonds, and means that it melts at a lower temperature. And also it will melt over a range, because those impurities won't be precisely distributed about the crystal. It'll affect some areas a bit more than others, so some parts will melt at slightly lower or slightly lower temperatures than others. So what we should see is that it's sharp now instead of over a range. If you've got impurities, it'll be over a range, and it'll be close to the data book value. This next one also came up in the other paper, really. With the chemistry of the OH group is a really commonly examined topic, and you need to know about different acidity of OH group containing compounds, and you also need to know various reactions of alcohols, one of which involves dehydration. So I'm just going to put the molecules here with this question. So the students make some predictions about salicyl alcohol. They predict that it will fizz with sodium carbonate solution. So we're basically saying, have we got an acidic group in there? Well, whenever we've got a hydrogen directly attached to the oxygen, we've got potential for a hydrogen ion to be lost, which means that it could act as an acid. But a phenol is a very, very weak acid, and an aliphatic alcohol, we don't really lose a hydrogen off there normally. The only group that would be strong enough out of these two molecules here to liberate carbon dioxide from a carbonate would be this carboxyl group here. Now, salicyl alcohol doesn't contain a carboxyl group. It only contains a phenol and an aliphatic alcohol. So we would have to say that the first prediction is no, it will not fizz. So it will not fizz. So we would say phenol and aliphatic alcohols don't react with carbonates. And for the second one, they predict that salicyl alcohol will dehydrate when heated over aluminium oxide to give a substance that will decolorize bromine water. So a substance that will decolorize bromine water has to contain a carbon-to-carbon double bond. So when we're dehydrating, that's an elimination reaction where we're pulling water out of the molecule. And when we pull water out of the molecule, we're taking an OH group. We also need to take a hydrogen. So if we look at typical alcohol, so look at something like this, what we could do is we could dehydrate this alcohol. We could take an OH there, we could take an H off an adjacent carbon, and in doing that, we would end up forming a double bond between those two carbons, and we'd release water. But if we look at salicyl alcohol, what we've got here, we're not going to be able to do it with this one, because it's directly attached to the benzene ring, and there's no hydrogens on the adjacent carbon. But similarly, this one that you might think there's a chance, there's a carbon here, but then we're looking for hydrogens on this carbon, and there isn't. There are no hydrogens on that carbon, so we cannot dehydrate. So no dehydration, since no hydrogen atom on carbon adjacent to the carbon bearing the OH group. Okay, they are giving in the mark scheme 1 for the no dehydrate and 1 for the explanation. Okay, and they're only giving 1 for the whole of that first explanation. Right, when salicyl alcohol reacts with concentrated hydrochloric acid, only one OH group reacts. Write the product, write the formula of the product formed. Okay. This here is a nucleophilic substitution reaction. That's what we're talking about when reacting with concentrated hydrochloric acid. We're not thinking acid and base reactions here, because remember the OH group is acidic itself. Well, in phenols anyway, and carboxylic acids. So if we just have a look at salicyl alcohol here, well, we have got that OH attached to the ring. Now, with the OH attached to the ring, you're not going to be able to substitute that, and we've not learned about substitution reactions with the ring. That will feel absolutely perverse to you next year as well, once you've studied benzene compounds. Because reaction with concentrated hydrochloric acid, well, as I talked about either earlier in part B or maybe in part A, the first thing that happens is that when you've got concentrated hydrochloric acid around, it means you can protonate the oxygen. You can add a hydrogen ion to it, and that makes this a far better leaving group. Now we've got a partially positively charged carbon there, and that can be attacked by a chloride ion. Now you could think about a chloride ion also attacking here at this carbon, but we've got a delocalized ring of electrons that would repel it, so you don't tend to get nucleophilic substitution reactions occurring off benzene rings. So this is where it will react, and if it does that, it just takes the place of this. So ultimately what we're going to end up with oops, I've drawn that wrong, sorry. We've still got the carbon there, sorry. And the chlorine comes off the carbon. Okay, so there's a CH2 there. Salicyl alcohol reacts with ethanoic acid in the presence of concentrated sulfuric acid. That should go straight to you right, esterification. Draw the skeletal formula of the product formed. Now the question here is, if we look again at salicyl alcohol, what this is testing is your understanding that phenols do not react with carboxylic acids. Phenols, although stronger acids than aliphatic alcohols, phenols are less reactive than aliphatic alcohols. the lone pair on the oxygen is partially delocalized into the ring, so it's less available for nucleophilic attack or something else. And we do have, though, the oxygen here on this hydroxyl group with its lone pair and partial negative charge. And if we had ethanoic acid around, then what we could get is this oxygen attacking this partially positively charged carbon here, and we could join these two together and start off the esterification reaction. So it's this one here that's going to be esterified. So when you draw this, we're going to draw the rest of the molecule exactly the same. So leave that phenol group. But then we go up to the carbon, down to the oxygen. And remember, when we form an ester, we lose water. Okay, so we lose the OH from there and we lose the H from there. So we've got that oxygen. That oxygen is now going to be forming a bond with that carbon. So it's useful just to remember what the first step in the mechanism is. We don't need to remember the rest of the steps. Then we go up to another carbon, double bond to an oxygen, and then down to the other CH3 there. So that's how that one there will look. Okay. And then the last one. So in a question like this, we've got to assess the different types of intermolecular bonds that could be formed. So the boiling points here of this one on the left, 197, this one on the right, 267. So we can state factually the intermolecular bonds must be stronger between molecules of this than this. Then we've got to go through what they are. Okay. So if we have a look at this, we've got similar sort of sizes and type and atoms. So therefore, the instantaneous dipole-induced dipole bonds are going to be of a similar strength. Both have got polar groups in them, so could form permanent dipole, permanent dipole. But also what we've got here is we've got hydrogen atoms directly attached to small electronegative atoms, oxygens. So we've got the potential for hydrogen bonding. So if we look at this one to start off with, we've got lone pairs on an oxygen, and we've got a hydrogen attached to that. So we've got both a lone pair acceptor and donor here, and we've got the same there. If we compare it to this salicylaldehyde, we have the same situation here in terms of this hydroxyl group. However, then we have an aldehyde here. Here, the hydrogen is not directly attached to the oxygen, so that group cannot form hydrogen bonds. So what that means is, on a per molecule basis, the salicyl alcohol can form more hydrogen bonds than the salicyl aldehyde. Therefore, the overall intermolecular bond strength will be greater between molecules of salicyl alcohol than between molecules of salicyl aldehyde. So we go something along the lines of saying the salicyl alcohol can form more hydrogen bonds than this. I shouldn't have used SA because that's going to be SA as well, but salicyl aldehyde as 2 times OH groups. I would probably say, which are the ones that are going to be participating in hydrogen bonding, or you can circle them there and then point to them, label them, etc. But it's better to write it in the text here because that's where the examiner will be looking. As 2 times hydroxyl groups, whereas the salicyl aldehyde only has 1. The aldehyde group can't form H bonds. Therefore, now, in this particular question, it's not giving you a standalone mark for saying, therefore, this one has stronger overall intermolecular bonds than this one. But it is good practice because, in 90% of the cases it is given. It's good practice to say, therefore, this has the overall stronger intermolecular bonds. Okay, that's why its boiling point's higher. So therefore, this stronger intermolecular bonds than this. Okay, right. Hope that was useful. Hope I didn't make mistakes along the way. And I'll see you all in college soon.